Hi guys. Okay, we are going to start into Unit 2. So in this folder, I have put the notes for Unit 2. So this is the entire note packet for Unit 2. You will also see in there the supplemental sheets file, and I would want you to print that off also. If you do not have printing capabilities and you need these printed for you, you need to email me to let me know. And I will leave a copy of both of these at the front counter at West, okay? So email me, make sure that you write, that you are in the online geometry class, and that you're needing copies of the note packet and then the supplemental notes also, okay? Unit 2 in geometry is very different than any math that you guys have seen before. This unit covers proofs. Proofs is a lot of writing. So this is not something that you've done in math. Think more of English. You're going to have to think through processes, and you're going to have to think through, why am I doing this and what would the next step be? So it's almost like doing a math equation, but telling me what each step is after doing a single step, okay? I think about this like brushing our teeth. There's so many things that you're used to doing when you're brushing your teeth that you probably don't realize how many steps that are actually involved. So then you have to think about, okay, if I were going to teach some 15-year-old person who's never brushed their teeth in their entire life, what would I need to tell them? Well, I would need to tell them that they need to go buy a toothbrush, then unwrap the package, then pick the toothbrush up, then grab the toothpaste. Then they need to take the lid off the toothpaste, then they put their toothpaste on the toothbrush, and so on and so forth. So you're doing every little step, and that's kind of what proofs are. It's explaining what you need to do in a certain order. Okay, so 2.1, we are going to talk about inductive reasoning. So in this unit, there are two different types of reasoning. There's inductive reasoning, and then there's going to be deductive reasoning. So inductive reasoning we're going to use or talk about today, okay? Conjecture. A conjecture is an unproven statement, but we base it on observation. So I could look outside and I could say, it is cloudy, therefore it is going to rain, okay? So we know what the sky typically looks like when it's about to rain. That is unproven right now, what I'm saying, but it might happen. And I'm basing what I'm saying off of things that I know around me and observations that I've made in the past. Inductive reasoning, so that's what I was talking about before, it looks for patterns, and then we make a conjecture. So we say, this is what's happening based upon the pattern, okay? And then a counterexample is a specific case that shows a conjecture is false. So I may say that every Wednesday at the school, there are no students here, okay? So that's just a conjecture that I'm making based upon there's no school for kids on Wednesdays. However, a counterexample to that would be, well, there were students here last Wednesday because they were taking the practice PSAT. So that proved my statement of saying there are no students in the building on Wednesdays wrong, because I came up with a counterexample, something to prove it wrong. Okay, on 1 through 4, I want you to pause me. And I want you to make a conjecture using inductive reasoning to say what the next picture in the pattern will be. Once you are finished with that, go ahead and unpause yourself. All right, this one, it goes 1 dot across, 2 dots, 3 dots. So the next one would be 4 dots and 4 dots down. Okay, number 2 splits into halves, thirds, fourths, so the next one would be fifths, and you want to try to split it as evenly as you can. This is not the easiest, I will tell you that. Uh-oh, 1, 2, 3, 4, yeah, I can do that, 5. Okay, there we go. Next one, the arrow faces a different direction every time, so it faces to the right, then it faced up, then it faced left, so then now it faces down, but we also have shading. So I have to make sure to get that shading in there. And then the last one is we have a square. The square is broken into 4 squares. Awesome game. So then we have one box that is broken into 4 of those. So we did upper right, upper left, lower left. So this one would be lower right. This box is shaded. I know it's really hard to see on your paper, but that one's shaded. Every time this shading switches, so upper left, upper right, upper left, upper right is where this would shade. Okay, so those are all using inductive reasoning. We're coming up with a conjecture on what we're thinking is happening in the pattern, and we're drawing the next one in the pattern based upon what our thoughts are. Describe a pattern in the numbers, write the number next to the pattern. Okay, so we go from 2 to 5, 5 to 8, 8 to 11. So what is happening there? What do you notice here? They're increasing by 3 every time. So then the next one would be 14, then 17. And then I would write down add 3. I want you to pause me and try 6, 7, and 8, and then I'll go over those. You have to be careful on these. Sometimes these are just like just a guess and check. There's not like a way that I can say, okay, this is what you do every time in this pattern. It's really more of a guess and check. So some of them will be more difficult for you. Some of them will come to you really quickly. So if you get to one that you're struggling with, I say skip it and then do the other ones and then come back to it. Maybe your brain has reset and you can think about it in a different way. Okay, so pause me, try 6, 7, and 8. Unpause me when you're done. This one, down 4, down 4, down 4. So down 4 more would be 11. So I'm going to subtract 4. 1, 4, 9, 16. This one, I bet some of you guys said that this went up by 3, by 5, by 7. The next one would be by 9. And that is true. However, what's 1 squared, 2 squared, 3 squared, 4 squared? So 5 squared would be 25. 6 squared would be 36. So squared.
Please pardon the interruption. Mark Kerp, please call
Numbers.
4010. Again, Mark Kerp, please call
Sorry.
4010.
Okay. If you did it the other way where you increased it by 2 every time when adding, that's fine. 3 to 0, 0 to -3, -3 to -6. The next one would be -9, and then -12. We subtract 3 every time. Okay, show the conjecture is false by finding a counterexample. So we're going to prove it false, but we're going to use a counterexample. So we're going to give an example of why or when it is false. So the quotient, you have to know what quotient means. That's an answer to a division problem. The quotient of 2 whole numbers is a whole number. Well, what if I did 5 divided by 2? That equals 2.5 or 2.5, and that's not a whole number. So that would be one counterexample. There's going to be many counterexamples that you can have. That's just one of them. Pause me, try 10 and 11 on your own, find a counterexample to each of those, and then unpause me when you're done. Okay, all prime numbers are odd. Typically, all prime numbers are odd. Most of the time, all prime numbers are odd because most even numbers, 2, will go into all even numbers, right? There's one even number that is prime, and that is the number 2, because only 2 in itself goes into it. So that's my counterexample to prove that wrong. That statement is now wrong. If the product, so multiplication, of 2 numbers is even, then both numbers are even. So like 2 times 4 is 8, 4 times 4 is 16, so those are proving it correct. But now I need a counterexample to prove it incorrect. How about like 2 times 5? Well, that equals 10, and that is an even answer, but not both of these are even. They are, one is even, one is odd. All right, next page. One more. This is a counterexample one. So we need to prove it wrong. The sum of 2 numbers is always greater than the larger number. So like 5 plus 3 equals 8. So sum means add. So the sum of 2 numbers, so 5 and 3, equals a number that is larger than my larger number here. So 8 is larger than 5. Well, there's a couple different ways I could think about this. If I add 0 to anything, it's not going to be bigger. So like 0 plus 4, that equals 4. 4 is not bigger than 4, it's equal to 4. Or what if I had added a negative number? It goes backwards, and so now I get an answer that's less than my original answer. Okay, on 13 and 14, I want you to write a function rule related to x and y. What that means is I want you to write a rule where y equals something that I do to x. So you talked about these in Algebra 1 in linear equations. So what do you do to 1 to get to 4? What do you do to 2 to get to 3? What do you do to 3 to get to 2? Same thing here on 14. You're going to do a y equals equation. What do you do to 1 to get to -5? What do you do to 2 to get to -3? What do you do to 3 to get to -1? And it has to be the same thing every time for it to work. These are tricky again. It may be some guess and check, and that is okay. If you get stuck on them, go on, come back to it so your brain has reset. So I want you to pause me, and I want you to try 13 and 14, and I truly want you to pause me and don't just listen to what I'm going to say next. I want you to actually try these so that you can kind of get a hang of what's going on here. Unpause me when you're done. Okay, so what's happening? So here I added 3. If I add 3 to 2, I get 5, so that doesn't work, just adding 3. Maybe I can do something to my x. What if I made it negative? So negative x, so that's a -1. How do I get to 4? It's add 5. What if I made 2 negative? So -2 to get to 3 is add 5. What if I made 3 negative? -3 plus 5 is 2, so that works. So make x negative, so negative x, but then you have to add 5. And then I could do a follow-up question on that, guys, and say, okay, what if my value of x was 10? So then you would plug it into this equation. -10 plus 5, well, that would give me -5. Number 14, I have 1 and -5, 2 and -3, 3 and -1. This one's a little more tricky because you're doing multiple processes. You're going to double the x value, so double the x means 2 times x. So 2 times 1 is 2. How do I get to -5? I subtract 7. Let's see if that works here before I write that down. 2 times 2 is 4. If I subtract 7, I do get to -3. 2 times 3 is 6. Minus 7 is -1. So that does work. Again, a lot of guess and check. You can do this. You are very capable to do that, okay? Bacteria growth. Suppose you are studying bacteria in biology class. The table shows the number of bacteria after n doubling periods. Your teacher asks you to predict the number of bacteria after 7 doubling periods. What would your prediction be? Okay, so what is happening? It is doubling, right? This bottom number. After every period, it is doubling. So they want to know after 7 doubling. So here's 6. I'm going to double 128, and I get 256. Then I'm going to go to 7. Okay? 7, if I double 256, I get 512. So it'd be 512. Okay? So on that question, you could do a formula, a function, y equals something, or you can extend the graph or the table that they have going. Okay? The half-life of an isotope is the amount of time it takes for half the isotope to decay, get smaller decay. Suppose you begin with 25 grams of platinum 191, which has a half-life of 3 days. That means every 3 days, it's half as big. So if on day 0 was 25 grams, that means on day 1, so this is day, this is grams. That means on day 1, it's 12.5. That means on day 2, it's going to be half of that, so 6.25. Oh, I'm sorry. Nope, that should not be day 1. Its half-life is every 3 days. So that's day 3. This is day 6. Day 9, it would be 3.125. Continue that until you can find when it's less than 1 gram. So 12 would be 1.5625. 15, so 3 more days, is at 0.78125. And then, there we go. So it would be at half of 1 gram after 15 days. Okay. What you are going to do right now, as far as homework, I'll be quick. You have a 2.1 Schoology, and then you're going to do this.